Okay, so we have 2 people per group, and we are going to present our proposal following the group order. So in the end of the semester, we will reverse the order. So let's welcome Junxiang and Dewanga for their proposal. Are they here? Oh, okay. Maybe we can wait. So let's move on to group 2. So when your teammate comes, you can jump in. Okay. So let's welcome the second group. So Yang, Rao, and Abis. I think better use the mic.
Good morning, everyone. Our project topic is manipulability and trajectory optimization. A case study on Coca KR70 R2100, presented by my name is Yamrat and my teammate is Adisu. So the contents of our project proposal is introduction, objective, methodology, timeline, and reference. Let us go in the introduction part. This project studies on the manipulability and trajectory optimizations of Coca KR70 R21 industrial robot. We proposed that an objective function maximizing the maximizations of manipulability based on the Jacobian matrices and obtain the optimal path while minimizing the energy consumption. So the goal of this proposal is to achieve the balance between the robot performance and minimum energy consumption through the Gregorian mathematical optimizations like Tekete condition and gradient-based linear programming. In robotics, robot manipulability is the capacity of the robot's arm or manipulator to perform the movements effectively and efficiently within diverse directions. It is essential to assess how the adaptively the robot can control its effector velocities, such as gripper or tool, within its operational spaces. Let us see the key aspects of robot manipulability. The first one is called freedom of movement, means the degree of freedom the robot is to process, or how the numbers of independent movements how the robot process. The second one is condition and singularity. In robotics, singularity means the specific position and configurations of the manipulator while its arm loses their positions or movements just to control it in a certain direction. The third one is isotropy and ellipsoid. Isotropy means the ability of the robot in equal S all directions to move within a certain direction. The last one is performance and optimization. We need to improve the performance characteristics of the robot manipulated like speed, force capability, accuracy, and efficiencies. Next part is presented by artist. Okay.
Good morning, everyone. So our main objective is to perform manipulability and path optimization of this Coca R200 2100 industrial robot. So through the optimization performance, we will analyze the kinematic and dynamics of this industrial robot, and we will formulate an objective function and set specific constraints. After formulating that, we will perform a gradient-based nonlinear multi-objective optimization technique for optimizing the parameters. And finally, we will validate the optimality of these parameters. So, since we will optimize two parameters, namely manipulability and path optimization, we will have separate and different objective functioning constraints. So, for the manipulability, the objective function, we will use the Yashikawa equation that is a function of this robot Jacobian matrix. So we will maximize this objective function, and we will have separate constraints. First, we will perform the optimization, the maximizing optimization by unconstrained method. That means the joint variables will have no constraints, and then separately we will perform a constraint optimization by constraining the torque and the joint angles. And when we come to the path optimization, our objective function is to minimize the total energy exerted by the joint actuators. And for the constraints, we will constrain the end effector position and joint parameters. So we will use gradient-based nonlinear optimization technique to perform both the manipulability and path optimization. And for subsystem analysis, we will use Python. And finally, we will use KKT or Pontagram's condition for validation of these optimal solutions. And for our project scheduling, we will have 4 quarters. So for the first quarter, of course, we will have a literature review in all of the quarters. So initially, we will do the kinematic and dynamic analysis of these robots. And in the second quarter, we will perform the manipulability maximization analysis. And in the third quarter, we will perform path optimization analysis, and finally we will document our results in the fourth quarter. So these are the references that we will use. We have used to prepare the proposal. That's all. Thank you.
Okay, so in your formulation, I noticed that you have 2 objective functions. One is the f of j, and the other one is energy. I think you can also look into how you can integrate both formulations together. So it's so-called the multi-objective optimization. So usually the most simple way to integrate them is to have a weighted sum formulation. Basically, W1 times F1 plus W2 times F2. So the W's are the weighting coefficient. And the weights are, when the weights are higher, that means that objective function becomes more important. So sometimes people will formulate a general form like this, so the user can decide, okay, now do I prefer better performance or greater energy saving? So usually there's a trade-off. If you want to save energy, sometimes you will lose some performance. So usually they are conflict with each other. So it's a very typical optimization problem in practice. Usually people try to find a balance between performance and also energy saving. So it's quite common. We can figure out, maybe check more literature review to figure out how people integrate them together. And it's actually very doable for what we have learned so far. But I'm quite curious about the constraint. in your formulation 1 and formulation 2, they are having different constraints. I think if you are having some limits for your, for example, joint angle in the first problem, that means in the second problem you may have the same constraint as well. So I think for both problems, they should have the same constraint. That's the limitation of your system. So that's why I recommend you integrate both. Maybe you keep all the constraints, or maybe you just drop some of them. Depends on how you formulate the physical situation, and try to combine both object functions. Other than that, you may need some kind of programming to figure out the kinematics and dynamics, like you said. Maybe you can check on the literature, program guide by yourself, or maybe there's already some open codes that you can learn from. Both are okay. The next thing you need to worry probably is to visualize your result. In Python, if you want to have visualization, you may need to spend some time to figure out how to make the drawings of the robot. If you want to have a really nice demonstration of the robot like this, then it's more complex for your programming. But if you are just making drawings of the a skeleton of the robot, then it's easier. So also that's another thing to make decision, how to visualize your result. And finally, you need to verify how the correctness of your analysis. So you also need to worry about whether what you have done is 100% correct. So that will be, I think, the key factors in this project. I like this project, so I hope to see good results at the end of semester. Okay. Comments?
As Professor Lin, as what Professor Lin said, I think the singularity of the robot is the key, most key of the robot movement. I think before you do something about basic optimization, you can try to understand what is the forward and backward kinematics and the DH model. I think it will be better before you do something about basic optimization.
Yeah, I think I agree. For the singularity, maybe you also need to put them in your constraint. You never want to move pass through the singularity position. Otherwise, you will lose control. Okay, great. Thank you. Let's thank the group. Is group 1 ready? Okay, so let's welcome group 1, Jun Xiang and Daewanga.
Good morning, well, group 1. Here is our outline, and we will do the introduction and talk about the mathematical model and methodology. So our research will be optimizing theoretical model of digital light processing in determining printing parameters of certain resolution. So this is about photo current 3D printing, and it's been a very important printing technology, and it's proved to be highly efficient and precise. But there's also some challenges the technology is facing. So the research shows that it is actually a complex process, and is already a lot of progress in understanding the relationship between the printing parameters and the final mechanical properties of the 3D printed object. But there are still many problems remain unsolved. So to further understand the process and achieve higher accuracy, it's necessary to consider the printing parameters and also to improve the model.
And going to the mathematical model, this will be our theoretical model. We assume that the equation S and polynomial order equation. This theoretical model represents the relationship between printing parameters, and this will be the meaning of the symbols. F will be the resolution, X LED current, Y curing time, and Z grayscale level. And we try to optimize P alpha, beta, and gamma, which represent the coefficient of the different order of polynomial order equation. The polynomial equation have different number of coefficient as showing in the table. And the next is, since we use experimental data, we have an idea to use sum of square errors in order to obtain the coefficient. And this is our objective function. And this is our workflow or flowchart, and we plan to use three methods such as Newton's method, steepleton, and conjugate gradient. And then we are employing that optimization to use and let the calculation converge, and the goal will be the coefficient in each end order polynomial equation, and the second one is to obtain the best optimization method. And lastly, this is our reference, and thank you everyone.
Okay, so which one of you is from manufacturing? No? So you just decide to
Yes, bro.
bring it. Okay. So do you have enough data for 3D printing?
Yeah, actually, right now about 12,000 data.
Try it, test it by yourself
Uh,
or from the paper?
no, this is from the other course, and
you have a course.
Yeah.
Okay, I see. So my comment is that basically you are trying to find the best fitting model
yes, bro.
to describe some kind of performance with respect to some parameters.
Yes, bro.
And you have some data. It sounds like you have some data amount less than 20, right? How many?
12,000, bro.
Oh, 12,000.
Yes,
Oh,
12,000.
okay. So I misheard. Okay, good. Then in that case, it's pretty good. You have a lot of data. Then I think you can try different models.
Okay.
This is a so-called a power law function. Maybe you don't need to have exact function form.
Yeah.
They could be second order polynomial,
Yeah,
or third order, fourth order, or you can look into something called kriging. But that's very challenging. In my lab, actually, I have a code of so-called kriging. It's a very highly nonlinear curve-fitting model based on Gaussian function.
Okay, bro.
So how to spell it? Kriging, kriging. So if you really want to work on something like that, I actually have some code. So I can share some literature with you and maybe share my code with you.
Okay, bro. Okay. Thank you.
Because if you have polynomial in certain order or a power law like this, usually the shape of the function will be, it's like predefined. It's only thing you're doing is trying to find the best parameter. But the ability of the function being able to fit the data is set.
Oh, okay.
So there's a strength of that. The ability level of that kind of function form is limited. However, if you use highly nonlinear model like Creamy. It's really able to fit all the data you want. The issue is sometimes it will be overfitted, too fit. Yeah, so the only issue you need to worry about Creamy is if it's too fit. Yeah. For those, it may not be fitted enough.
Okay.
Yeah, so like what you're trying to do, you are trying to minimize the sum of error or sum of square error. Of course, if you choose a model and then you figure out, okay, you already reached the minimum, but there's still a huge amount of error, that means this model is not good enough.
Okay.
And if you are trying to work on this, you may also look into some statistical analysis such as ANOVA, ANOVA, ANOVA. So there are statistical standard procedures to figure out how well your model is. So usually they will figure out, okay, how well it is, then if it's not, they change the model until they repeat this until they find a good one.
Okay.
Yeah. So you may need to find some book, because whatever you are trying to do is very standard already. It's well established in statistics. You can look into them. And also, you are only choosing 3 variables. Maybe you can check whether your data has more parameters.
Yes.
Yeah, so once you are done with your modeling, the next issue would be how to verify the appropriateness of your modeling. So there's something called cross-validation. Because when you have a bunch of data, when you throw them in your model, at the end you have some resultant model. You need to check how good it is.
Okay.
So there's one way to cross-validate is to separate the data into maybe two parts. One chunk is larger, maybe like 80% of data. The other chunk, for example, 20%. So you use the 80%, which was randomly chosen for training your model, and the other part, 20%, for testing how accurate it is.
Oh, understand.
Yeah, so sometimes people do that. And people even figure out a way to randomly select the data so you are not trapped inside the data. Yeah. So look into more references and figure out what people have done. There are even something called tenfold cross-validation, which means they randomly separate the data into 10 parts. And they will repeat this process 10 times. Every time, they pick up 1 out of 10 for testing, the other 9 for training. So the 10 parts will be chosen as the testing part by turns. So it's like a 10-time process. And they will figure out, if I really randomly figure out how the accurateness of the model by such a random process, do I get good results for all times? So there's a lot to learn for if you are looking to this.
Yeah.
So look into how to do approximations of the function, and then some statistical modeling, and also, like I said, cross-validation. Okay.
Thank you, Robert.
Next page. I think this is index of cost function of cost function. I think you need to understand the physical definition of it. I think it will be better for you to know what optimization you work on.
Okay, thank you.
Okay, okay, great. Let's take the group 1. And now we will welcome group 3, Yijun and Lise.
Hello, Professor. Hello, everyone. My name is Liu Yijun, and usually talking about genetic algorithm selection and crossover operator analysis. In this contents, introduction, flowchart, different types of selection, different types of crossover, feature fitting, and reference. Introduction. The genetic algorithm is based on drawings theory of natural selection and has developed of 4 operators: selection, reproduction, crossover, and mutation. The genetic algorithm encodes data into string called chromosomes, which develop continuously to select better chromosomes, reducing the fitness value until convergence. The key difference between this algorithm and Newton method is the ability to define the optimal solution from multiple points, whereas Newton method only works from a single point. And you can see picture below. We wanted to test different genetic algorithm selection and crossover methods and conduct coordinate analysis to find the fittest algorithm. And then we use this algorithm to the picture fitting, like lifestyle. Flowchart. First, there will be an initial population. It's containing many different chromosomes. In the second step, calculate the fineness of this population. Determine if the termination conditions are met and check for convergence if conditions are met, and obtain the optimal parameter solution. If the conditions are not met, proceed with selection the better chromosomes from this population for crossover. Like 2 chromosomes into the 2 parts, and combine them from the pairs new chromosomes. The final stage is mutation. Define a mutation rate and uniformly distribute probability values. If a probability value is less than mutation rate, the mutation randomly select a bit from the chromosomes and fit it from 0 to 1 or from 1 to 0. And finally, obtain a new population and return to the step of calculation finance to the new chromosomes.
Hi, I'm Rich, and we continue the presentation. And in the process of the genetic algorithm, there's a few stages have multiple methods like selection part and crossover part. And the goal of our project is to analyze the genetic algorithm in these different methods. So following, I will introduce different types of crossover. Here we choose 3: single point crossover, 2-point crossover, and uniform crossover. And here we can see two binary string on the screen, string A and string B. And in genetic algorithm, we call them chromosomes. And chromosome is a string of symbols, and usually there are binary bit string. And so here we can call them chromosome A and chromosome B. And each element in the chromosomes, like here, the 1 or 0 are called gene. And here we are going to create new chromosomes from this chromosome A and chromosome B. So we refer to chromosome A and B as parent, and new generated chromosomes are offsprings. So let's see how single point crossover works. So the first thing is to randomly design the crossover point. Like here, we shown as a green arrow here. Then we copy the genes from the parent. Then the next is to exchange the genes after the crossover point. And this is the single point crossover. And next crossover is 2 points crossover. This one is quite similar with the previous one, but here we randomly pick 2 crossover points. So the first, and then we copy the genes from the parent, then switch the genes between these 2 crossover points. And this is called 2 points crossover. And next is an uniform crossover. This one is a little bit different because before the crossover, we have to randomly generate a new string of new binary bit string. And here we call it mask. And if the mask is equals to 1, means in this section, in this position, the genes has to be swapped. And this is called uniform crossover. So except for the crossover, we still, in the selection part, we still have multiple methods. And here we also introduce 3: relay wheel, tournament selection, and elitism. And the purpose of the selection is that each chromosome have fitness. The higher fitness means it's more close to the optimal solution, which means these chromosomes more likely to have superior genes. So we want to keep the good genes, right? So it should be good genes combines to good genes and produce more good genes. But it doesn't mean that we have to kill the genes that is not good. Because if we did kill all the bad genes, it means bad chromosomes, it means it might lose some diversity, and it might leading us to the local optimal. And so that's not what we want. So we want mostly the crossover happens from the good genes, but we still have to have some chance for the bad genes, chromosomes. So how we did that? Introduce relay wheel. So the table on the left-hand side is an example, and in reality we should have more chromosomes, but here we just took 4 for example. So here we can see the chromosome 0, 1, 0, 0 have the highest fitness. So it has the highest probability in this relay wheel. So when we start the relay wheel and we select, and now we select 0, 1, 1, 1. So 0, 1, 1, 1 can be reserved to the next iteration. And we start again, select again. Now we select 0, 1, 0, 0. So these 2 selected chromosomes can be survived, and other chromosomes will be deleted in this iteration. And next selection is called tournament selection. It also use the relay wheel, but it's a little bit different. For example, here we assume the first two chromosomes have been chosen by the relay wheel, but here the tournament part appears. We only choose the highest fitness one, and another we deleted. And for the next round, we still randomly choose two chromosomes, and also we only save the highest fitness one. So here, the middle two is reserved for the next iteration. And the final one called elitism. Elitism is, I can say it's exactly the same as the relay wheel selection. But because it's elitism, so before the relay wheel, he makes sure the most highest finished one can be reserved to the next. Then, after make sure of that, then do the relay wheel. Here, we got the smallest finished one, but yes, these two, the highest and lowest in this condition, we can reserve them into the next interaction. Okay, and we introduce a lot of methods of crossover and selecting. So we are going to test them into picture fitting. And picture fitting is that the picture on the left-hand side is the target image, and right-hand side is the progress of genetic algorithm. So at first, we generate a random picture and put it into the algorithm and make them to get close to the target image as soon as possible. And that's how I plan to do it. So this is the target image, right? So the first thing is to flatten all the blocks. And next thing is to encode them into binary bit strings, where the white block represents 0 and the black bar represents 1. And here we can get our target chromosome. So we have to randomly produce a lot of chromosomes. The length just as long as these target chromosomes, and started put them into the genetic algorithm and to see how fast they can converge. They can become exactly the same picture. And just like I just introduced, we pick 3 different types of selection and 3 different types of crossover, and it can create 9 combinations. So we are going to test this picture fitting project and with these 9 different combinations and see which one is the fast, which one cannot converge. If they cannot converge, which percent they have reached. If they can converge, is it converge like this or converge like slowly up to the optimal one? So these are our reference, and this is our proposal. Thank you very much.
Okay, a very detailed presentation. Thank you. You covered what I'm going to teach next week.
Oh, we just covered yesterday.
It's good. It's good. So thank you for your introduction to GA. So one thing is about the problem you choose. You decide to do the picture fitting problem. How are you going to evaluate the fitness?
I'm going to evaluate the fitness with the
Difference?
difference in error.
So lower difference, better score.
Yes, so in this case, the lower fitness is the best. And when the fitness equals to 0, then it means it's the optimal one.
Okay. So there will be, I think it's a definitely your GA can find a solution. I would say.
Try.
You may see an issue. You are going to try 9 different combinations of methods you are going to tests,
Yes.
and if you run the code, for example, 9 of them, and every code you try, for example, 10 times repeating. So you tested 90 different codes.
Yes.
At the end, you may not be able to find a conclusion
Oh.
because a GA process is very random. It's a process by luck. So sometimes the combination 1 is good, sometimes combination 2 is good. So even the combination 1 you try 10 times, their performance is always different. So, and also, even you find some kind of conclusion, okay, combination 3 is the best for picture fitting. Now you change a different problem. Maybe it's not the best anymore. So usually in GA, it's hard for someone to say this is the best GA. No one says that because it's really a process by luck. And besides the methods you choose, there are also some parameter to choose, which is the mutation rate, crossover rate, all the rates for your parameter. And sometimes they change the result so much because those rates allows more randomness or less randomness. Sometimes if your problem has a lot of local minimum, then you need a lot of randomness because you want to jump out of the local minimum. But sometimes when your problem is more smooth, the function is more smooth, then you don't need a lot of randomness. So GA is very tricky. So I worry maybe you at the end cannot get a conclusion. And another thing is picture fitting problem is interesting but also boring. Interesting for students, it's fun, but no practical impact. So my suggestion is I will share a code with you. It's a code that was written probably 20 years ago by my junior in my lab. Her thesis was about finding the best mechanism, like a full body teaching by GA. And I would like to see you to try her code with different combination of methods by what you want to do. But it's a more practical problem. So maybe try the picture fitting and also try my junior's code. So you have two problems to test. And maybe the conclusion will, I hope that will help you to find better conclusion. My junior's code is in MATLAB. So if you want, maybe you can already use that MATLAB code to do picture fitting because all the GA parts is written properly. All you need to do is to modify the crossover methods, mutation methods, and stuff. Because we don't, in that code, we don't try different approaches. We don't even change the crossover rate. We're just lazy. Okay, here's my parameter. We never touch it. Yeah, but if you want to touch those parameters, yeah, you can try. Okay, I will share that with you after the class.
Thank you, Professor.
Any comments?
And also by tuning parameters, like tuning parameters for the rates.
Yeah, there are actually a lot of parameters to tune. But you cannot test everything. If you try everything, there are too many combinations.
Yeah, GA is a useful method to search optimization point. GA uses multi-point to search one point. Yeah, so like what Professor Lin says, the parameters is important, like such as mutation rate or crossover rate. If you choose you choose high rate, this population or this round, the optimization point will be hit, and the next round it will be hit. If you choose low rate, it will always stay hit. So the parameter needs to define first before you use the GA. Okay,
Sometimes the parameter is even more important than the method. Okay, great, thank you. So let's welcome Group 4, Yujun and Emma.
Hello, we are Group 4. Today our topic is optimizing his design for CPU cooling system. In modern electronic efficiency, thermal management is essential to ensure optimal performance and lifetime of electronic components. Heatsink cooling has become a key technology to minimize the excess heat generated during the operation of electronic equipment. While a certain amount of heat generation is avoidable and considered normal, excessive heat can pose a significant threat to the performance, reliability, and life of electronic equipment. When electronic components are operated at high temperature, several adverse effects may occur, like performance degradation and shorter life. And variable components within an electronic device generate heat. Some of the major sources of heat include CPU, GPU, and IC. And what is heatsink? A heatsink is a passive cooling device. The main purpose is to transfer the accumulated heat from the electronic components to which is connected and dissipates it into the surrounding environment. And how is heatsink work? Heatsink work on the principle of heat convection. When the electronic components such as CPU or GPU operate, it generates heat. This heat is conducted through the metal or semiconductor substrates of the components and then transferred to the heatsink through direct contact. When heat reaches the heatsink, it spreads to its surface area. The larger the surface area of the heatsink, the better the heat dissipation and the more efficient the heat dissipation.
Okay, so for this project, we will use heatsink look like this. So we plan to make heatsink straight here. So the parameter will be the width of the heatsink, length, the base thickness from this one to this one, and then fin height, fin thickness, and space between fins. Which this variable will be affect the resistance of thermal of this heatsink. Then it will be affect the increasing power of the system. So in general, it will be look like this. So the CPU in below. It will be we will get high temperature here, and then with heatsink we hope that the heatsink will be lower the temperature and it will make the system more optimized. So the interesting part here is that the heatsink has fins and base, where the fins will have combination between the conduction and convection. So it will be affect the result of resistance of thermal. And that one we want to optimize later. So it will be look like this. This is where the CPU first, when the CPU get the input power, the temperature will be high, and then with heatsink, it will make the temperature lower. The lower pH will give more. It will create. It will have. It will handle the increasing temperature. Yeah, so here we want to minimize the delta T of the system. So we want to minimize the increasing temperature of the system with the power input multiplied by the RTH, the heatsink thermal resistance. So we will find the overall resistance of heatsink, and then we get the result. And what I expected here, we want to get this one. So the delta T, if we don't use heatsink, it will be go straight up like this. But with heatsink, we want to make the delta T as minimum as possible. That's what we plan to do here. So this is our reference. Thank you very much.
Okay. So both of you are my students, but I don't know you guys are interested in heat transfer.
Actually, this was based on my bachelor project. So
I see.
Yeah.
So when I started as a professor, I tried to avoid topics in heat transfer because I don't like it. But somehow, some of my students keep on trying to solve heat transfer problems. So I recommend you to read some of my previous publications. There are so many of them. It's about heatsink design. And then I think your formulation is too simple. So usually in practice, the heat distribution in the entire heatsink design is not uniformly distributed. So there will be local heat source issues, and also heat dissipate from the side actually. So it's if you use the equations you have, you are like treating it as a simple problem, but in fact the heat transfer inside is very non-uniform. So I would say if you really like this topic, you should build a CFD model, truly model it. But the issue is whenever you build a model and run it, it takes some time. Every function call costs you 10 minutes or 20 minutes, and every redesign costs you 30 minutes or an hour. For optimization, if you need 100 function calls, then it's very troublesome. So in our lab we have Smart Do. That's another tool you can touch that helps you to iterate. So I think if you choose to do CFD and Smart Do, that means your main focus will be on novelty. How would you like to define the geometry, and how would you like to choose the parameter in a novel way, so you can build something at the end which is something new, something maybe human cannot think of. There are even someone solving this problem by something called topology optimization. Topology optimization. But it's an even tougher field to work on. But I would say this topic right now it's interesting. It's well established in the field. For what you present right now, it's a little simple. I think it's a little simple.
Yeah, this is only the rough idea I made.
So I would say look into the topic and make decisions. Think of this as a topic that you can maybe somehow publish somewhere.
Okay.
Then it needs some kind of novelty or complexity.
Okay, perfect. Sure. Thank you.
Okay, any comments?
I think you have optimization function, but code. This
Son?
one.
Yes.
So I think I can see a relationship between the functions and your heat parameters.
Actually, from resistance thermal, we get the resistance thermal from the design of heatsink. So the difference define parameter of heatsink, it will be give difference number of RTHs. So it will be change everything soon. But yeah, in here I didn't define because it will be different if we change the design. Right.
Basically, everything right now is assuming everything is isotropic, everything is
that's true.
the same everywhere. Then
You have to read more literature for design variables, selection of the design variables.
Yeah.
So it's a very simple one.
yeah. Or like I said, run the CFD. Then you will
Okay,
see,
sure.
oh, this
Yeah.
even the and also when you run the CFD, usually the issue is how do you define the boundary condition?
Yeah.
Do you treat the heating surface as like a uniformly distributed heat source? But in reality, it's not. So how would you like this to be as realistic as possible?
Okay, I understand.
Yeah, but if you want to formulate some kind of non-uniformly distributed heat source in CFD, it's very troublesome.
Yeah, I will think whether.
Yeah. So anyway, look into more papers. If you need some reference, I can show you.
Thank you, Professor.
Okay, anymore? No? Okay. Thank you. So let's welcome the next group, Gong and Yao Zhong.
Good morning, Chris. Good morning, everyone. My name is Fong, and this is Isaac, my teammate. So our topic is focus on the maximizing of the bonding strain for hybrid paper and polymer microfluidic devices. And I'll talk a bit about the motivation of why we're choosing this topic, and also the methods we were going to use. So the motivations. So nowadays we need a lot of point-of-care device, which means the device that you can use for some common application like disease detection, or you can see here's the blood glucose testing kit. And this kind of device we can divide into two types, which is based on the main mechanism inside the device, which can have paper-based or polymer or plastic-based. And each kind have their own benefit. For example, the paper-based, we can manufacture with low cost, and it can also be biodegradable. Or for polymer or plastic-based, it's really durable, and it can withstand a lot of type of chemical. And so people start to think, how about we combine them together? So maybe we can have more applications. There's a lot of method to combine the two structures together, and one of them is called bonding. And in our topic, we focus on the oxygen plasma bonding process. And in this process, our substrate will for the polymer and plastic base, we focus on the PMS, and for the paper base, we focus on the photocurable resin coated paper, which means it's not a blank paper. It has some resin on it. So we try to actually the problem with that, we try to bond the polymer with the resin inside the paper. It's not directly with the paper. Yeah. So the process will be something like this. We treat the polymer or the plastic surface and also the paper surface with oxygen plasma, and then we try to stick them together, and we will try to evaluate the bonding strength. There's in the oxygen plasma bonding process, there have two important factors. This is the plasma time, or T, or the oxygen flow rate inside the plasma chamber. And we usually investigate the oxygen flow rate through the pressure, the vacuum pressure value inside the chamber. And based on some literature review, we see that people focus on the range for the time from 1 minute to 3 minutes, and for the vacuum pressures will be around 600 to 1000 millitorr. And our objective is that we want to find the optimal point of the time and also the pressure or the oxygen flow rate to achieve the highest bonding strength. And the bonding strength we evaluate based on one of the really common ways to evaluate the bonding strength for the microfluidics is that it's called burst testing. It's basically we close the V2 here, the valve 2, and we pump the water inside of the device, and with the closed valve, the pressure will build up inside the device, and at a certain point it will break the device, and that's the limit we have. We suppose that the bonding strength and the time, also the pressures, this will have some relation, like Jerry, like this. With A, B, C, E, and F is the weight constant, and because we don't know actually what is the function, so we use some design experiment which we focus on the response surface method. Especially the phase center central composite design to limit our number of experiments and then we will use that data to have the rejection equation, and then we base on that, and also based on the actual value of the waste content, and then we use the programming, linear programming or corrective programming to find the optimal T and P that having the highest bonding strength. Yeah. And we suppose that function, this will have the contour plot and also the surface plot, something look like this. And we try to do this. Thank you.
Okay, so I was smiling because you are working on something I worked on 20-something years ago. It's my master thesis. So I was working on PDMS bonding with oxygen plasma bonding. It's a topic I hate a lot when I was a master student. So one question, do you have the oxygen plasma bonding machine?
Yeah.
You have it, okay. So who's your advisor? Chen Pijun.
Yeah.
Okay. So for this kind of experiments, one issue is you need enough design of experiments. So now you have 2 parameters. How many tests are you going to build? 25?
9, that's actually.
9, 3 by 3.
Yeah,
3 by 3. Maybe that doesn't show you good enough function. But of course, you will see something. You will definitely see something based on the model you have. I will recommend you, because the quadratic function you use has the term of P times T. So P times T doesn't guarantee you to have a nice function. Sometimes it's like a, how do you explain it? It's not always following the same direction, so-called it's hard to explain in words. So sometimes when you try to do this, we sometimes will avoid the term of P times T. But we will see. At the end, I recommend you to plot the design points out. So in the next picture, you should have 9 points in the space. You may want to see how it really looks like. Maybe the function you choose is not the best model sometimes. this kind of research is very challenging because even for the sample you make, it's a very a lot of uncertainty. So if you make 5 different devices, their bonding strength may be a little different. So a lot of variation. So it's a very challenging problem. Does your lab already have PDMS and the paper with the resin coating? Does your device allow you to use this many materials?
It's actually my
Your thesis work. Okay, then I will share my thesis with you, so you can take a look. In my thesis, I didn't use the burst test. I used something called a bubble test. We form a bubble by pumping the air into the device. But I think for your case, burst test is better because your purpose is to make microfluidic system. So the boundary condition is similar to your final device. So, okay. Maybe later on when you have issues, we can have more discussion. Okay. Any comments? Okay, great. Let's thank group 5. And let's move on to group 6. Zhe Xuan and Billy Young.
Morning, Professor and everyone. I am Vinyan and my name is Jason. Today we are going to present our proposal, and our proposal title is Optimizing Wall-Building Parameter for Enhanced Hydrogen Storage in AD System Magnesium Matrix. This is our title. So we have introduction, objectives, parameters, and methodologies here. So I'm going to introduce about a little bit about hydrogen. Why we need hydrogen and why we need hydrogen storage. As you know, our world is in danger because of the pollution resulting from the burning of fossil fuels. So these fossil fuels not only pollute our environment, but they deplete throughout the time. The accumulation of these fossil fuels are deplete throughout the time. So governments around the world are searching for sustainable and green emission energy. So hydrogen is the perfect kind of energy carrier because hydrogen burns clean, and we can produce hydrogen from water by electrolysis process. So hydrogen is perfect kind of source because it is sustainable and it is green emission energy. Hydrogen is undoubtedly a good source of energy for our future Earth, but there is some challenges. The challenge is a storage challenge. So we have to find good hydrogen storage material, and researchers are propose metal hydride for storage of hydrogen. And magnesium is best choice for storing magnesium because it's a capacity of 7.6 weight percent. It can store 7.6 weight percentage of hydrogen, and this is a very low cost as compared to other elements, and also it is abundant resource, and it is lightweight. You can embed this magnesium metal hydride into our vehicles, so our vehicles can run with electricity. It is an energy carrier. But magnesium also has its own drawbacks. The drawback is magnesium is high thermodynamic stability. As you see in this image, in order to charge and discharge hydrogen, we need some amount of energy. But magnesium has high thermodynamic stability. Its activation energy is above 200 kilojoule per mole. That means it needs a high amount of energy to trigger or to start the reaction here. So It is a drawback of magnesium, and one of the drawbacks is slow kinetics. Slow kinetics means in order to discharge and absorb or dissolve hydrogen, it takes a long period of time. It is bad for storage system, so these drawbacks should be improved. So to tackle this problem, researchers are using different methods. The first one is doping with catalysts. They add different types of catalysts in order to improve those drawbacks. And alloying is the other method. We can alloy this magnesium with different type of elements. Making example, aluminum is one of alloying element for magnesium. Nanostructuring also one solution. Altering the microstructure of the surface of magnesium will enhance the storage performance of magnesium. And the fourth one is severe plastic deformation. By mechanically deforming the material, we will induce fine grain boundaries and more dislocation density, and these properties are very good for storage performance. And today we are going to discuss about the last solution, severe plastic deformation. In severe plastic deformation, our lab mainly do ECAP, equal channel angular pressing, and high energy ball milling. And our optimization is concerned on high energy ball milling technique. I will give you some introduction about this. This ball milling is mechanical processing technique used to produce fine powders and modify the property of materials through the intense mechanical deformation. So this GIF is somewhat explain what is ball milling. This ball milling is such kind of machine. We put our powder and balls in this jar and rotate this powder in order to refine the powder. So for milling, for ball milling, we have different parameters. One of the parameters is milling speed. The milling speed is after we put the samples and the balls inside the jar, we rotate in high speed, in high RPM. So milling hour is for how many hours we can mill our samples. This is one of our parameters. And finally, the pole powder ratio. Pole powder ratio means how many gram of balls are needed for our sample. For example, if you are going to use 10 ball powder ratio, for 1 gram we need to use 10 grams of balls. This is the parameter for ball milling. So what is our objective? Before going to our objective, I am going to give some introduction about the paper that we are founding for getting experimental data. This is high energy ball milling induced crystallographic structure change of 8661 magnesium alloy for improved hydrogen storage. This is the paper we are extracting the experimental data. So this paper objective is to investigate the effect of high energy ball milling on 8661 magnesium alloy. And this paper identifies milling parameters for ball milling machine. So after setting those parameters, they do hydrogen test on the resulting powder. After that, they compare. They are not doing optimization. They compare the structure and the storage property of those parameters. They have set parameters. Based on those parameters, they do ball milling. On the resulting powder, they do storage capacity. Then they compare which sample have shown good performance on storage. So these are the experimental parameters that are used for this paper, and they use speed, time in our ball to powder ratio. For speed, they have 3 levels: 300, 400, and 500 RPM are used. For time, 10 hour, 20 hour milling, 6 milling hours, and 50 hour of milling. And ball to powder ratio, they are used 10, 20, and 13. And the fourth parameter is milling agent, but it is common for all the samples, so we ignore these parameters. So our parameters are these 3. But our goal is to develop a governing equation for these parameters and find out the optimal pointers for maximizing storage capacity. Our aim is to maximize storage capacity. So we are going to find pointers to maximize the storage capacity. Then on the resulting parameters, we do ball milling, then we do hydrogen test. It is our goal for the project. So what are the parameters and the constraints for our proposal? And as I shown you before, these are the parameters, and this is storage capacity, the response. And these are independent variables. We change or fix these parameters, and we'll get the storage capacity is response. So These are response, for example, for 300 RPM and time 20-hour beating hour, and water powder ratio 20, the storage capacity is 4.01 weight percentage of hydrogen. These parameters have capacity to store this amount of hydrogen. So based on this, we have 9 samples. After that, we put constraints. So in these constraints, the speed should not be greater than 500, and the time, the beating hour should be kept below 50 hours, and water to powder ratio should be less than 30, because these experimental data are done on this area, area. So we have to use constraints like this. After setting these parameters, what experiments we are going to use in here is first, we develop objective function. We are going to use response surface method, and here we are going to implement design expert software to predict the objective function. We already tried the objective function, and the objective function here we find was non-linear, exactly non-linear. And for linear equation, we use linear programming optimization technique. So after computing the optimization, we found optimal parameters. These parameters are going to maximize the storage capacity of the hydrogen. So based on those parameters, we set our ball milling machine based on those optimal points. So the machine we are going to use is ratchet planetary ball milling machine. So we do ball milling. After that, on the resulting powder, we are going to use hydrogen test. We use several type of apparatus here. This is all about our proposal. This is our reference. Thank you.
So some questions. You chose 9 design of experiments out of possible 27, because 3 levels for each. So all the possible combination will be 27, right? So do you want to try all of them, or you can only do none?
We are going to use those experimental data we have found from the paper.
So basically you are not going to repeat any experiment.
Yeah.
Just get the data from the paper.
Yeah.
So what happened to some of the empty results?
On the paper we only found this storage capacity.
Yeah.
I have wrote email for the author. He is found in this campus, so maybe I'll contact him in person and they'll ask for those results.
I guess if you try to figure out other values, maybe the blank means no result, or I don't know, for some reason no result, or maybe he needs to repeat the experiment in order to get the data. So the issue of your proposal is that you have very little data. Yeah, and from here you can already say, okay, number 6 is the best.
Yeah.
Then there's no need to do optimization.
But after optimization, we found another combination.
But if you want to build a response surface, you need more data. 9 is very limited. So your model would be not very accurate.
Yeah, we have tried it, and the error square value is around 0.95, which means
the error is small.
Very big.
Error is big.
Yeah, no.
The error is small or big?
Small.
Okay.
It can't really 95%.
Okay. So, but you only have 4 data.
No. I will ask him, and I will go to his office, and I will on the.
But you said you already tried.
I wrote email, but he didn't respond.
No, you said the model was already.
Yeah. The model, I put bias some points here.
Oh, some gas.
Yeah, and I tried with response surface method.
But that's something you guess.
Yeah.
Right? Because the design space is a 3-dimensional space, and if you evenly distribute them and choose 3 levels for each variable, you are supposed to sample 27 points
Yeah.
in order to cover the entire space. So who knows, maybe the function is very nonlinear. Then you may have a large error.
Yeah, but they are not using 27
I know they are not using, because in this field, every experiment is very expensive.
Yeah.
So I'm just telling you, this may not be a good topic for you, because you don't have enough data. The purpose of this course is to practice optimization.
Yeah.
And if you have not enough data, you have nothing to do. Now you only have 4.
No, I think
Even you get 5 more, you don't.
this paper is
Are you in this field?
Yeah.
Okay.
And the
I guess
paper
that's
also
why.
this stuff.
I guess that's why you really want to work on this. But really, with data like this, there's really nothing to do. And the issue is, later on you may need to spend time to create data, and you may not have enough time. Maybe from the lab you can check some other papers. Maybe there's a time when someone already get a lot of data. That would be a better data set. Yeah, otherwise, I worry at the end you may not be able to showcase how optimization help you. And maybe the result is very obvious. You don't really need optimization. So it's like for the optimization course, you cannot showcase anything. And the issue is because you chose some experiments with very little data. So it's like you have nothing to play with. Like the other group, they have 12,000 data. Then okay, there's a lot of data to work on. Problems like this with columns of variables and columns of responses are very common. You don't really need to work on something that is having such little data. And data, you can easily find some other research with a lot of data. Or you can look into the literature. You don't really need to look at your professor's data, maybe some other similar field. There must be someone who has done a lot of data. You can focus on that. That may be helping more than this one. I just worry.
We have tried showing this. Our response of this section of the intercepts and see the coefficients.
Yeah, it's a response surface, I know. But I'm just saying the data is not even every method can get you some result. But if you have a greater space but very little known knowledge from the space.
Your question is the objective function will not predict good?
Because there's nothing to prove. Usually if you build a response surface, you want to show how accurate your model is. You need enough data to show. Right? Let's say you take one out and use 3 of them as your training, and then use 1 for testing. At the end, you may get a pretty poor result. Trust me. Just trust me on this, okay? Yeah, and also, can you go to the optimization flow that you presented here? So your response surface is a nonlinear function. And then over here you decide to do linear programming. So which part is wrong?
This one, linear programming. Linear programming.
But your response surface is nonlinear.
No, I think that's here.
So you're going to use a linear function?
Yeah.
Then your problem is super boring. The experiment you built definitely is nonlinear. It's okay to have nonlinear response surface and using linear program. You need to use sequential linear programming. So your sequentially making linear approximation, and so your design point move from your initial guess and then move to a position that is closer to the solution, and then you do approximation again. But every time you do that, you need data. Remember in our class, we have done that so many times. You need to do, you basically need data. Yeah, so for the problem you have very little data. That's an issue. So that's just my recommendation. Okay? So you better go back and think about it. If you want, you can arrange some time with me, show me more. Maybe we can find a way to improve what you can do in the class. Okay? Okay, thank you. Next group. There's group 7, Yanru and Nathaniel.
Good morning, everyone, and we are Group 7. My name is Cindy and he is Nate. Our topic is stability control of a heavy truck using quadratic programming based on MPC with control allocation technique. And this is our outline. We divide as introduction, problem definition, objectives, methodology, materials, conclusion, and reference. And for introduction, we'll go over accident area critical safety concern for heavy trucks. And for MPC is model predictive control. It is an adverse method of control that utilizes a system model to predict future states and optimize the control inputs over a finite horizon. And control allocation is pivotal in systems where the number of control factors is as the control objectives. And quadratic programming efficiently handles dynamics nonlinearities. And we're using a combination of MPC by QP with control allocation to optimize control actions for heavy trucks and prevent accidents. And our problem definition is that traditional control systems for heavy truck are reactive and do not adequately adjust the dynamic factors leading to rollover in heavy trucks. And the figures it shows the different vehicle accidents due to stability problems. And the aim is to design to predictive systems using MPC to mitigate rollover risks and enhancing road safety for heavy trucks. And our objectives first is that to track a desired yield race trajectory to ensure the vehicle follows a specific angular path around its vertical axis, and then minimize the vehicle's slide slip to reduce lateral deviations to maintain the intended path.
Okay, so I will continue to the methodologies, how we will tackle the problem. First, to optimize the control action, we have to model the vehicle dynamic using a 4D vehicle model. So basically the 4D vehicle model, we use the lateral and the longitudinal yaw and roll motions. So as shown here in the figure, we have the four-tier modalities, and the forces, the velocities, and all the parameters applied here are shown, and we'll try to optimize the yaw rate and the the yaw rate and the side slip angle beta for our case in order to maintain the stability of the vehicle. So the fundamental equation for yaw motion is derived from the sum of moments about the center of the vehicle is to be 0, and the yaw moment inertia times the yaw acceleration must be equal with the sum of all the torques at the center of the vehicle. And using this governing equation, and the other, the tire slip angle can be calculated with this equation. And combining all this together, we can find or the equation of motion, a nonlinear equation of motion for the yaw rate and the side slip angle beta this way. And we have to linearize this nonlinear equation using the first order Taylor series expansion and rearranging the equations and put together in a state space model, we will get this form. So after modeling the vehicle dynamics and linearizing the equation, we'll go to model predictive control. Here it defines an objective function that typically minimizes the difference between the predicted states and the reference trajectory along with the control efforts. So we'll minimize with this equation the objective function, which is subject to the states in the maximum and the minimum states of X and the maximum and minimum input variables in which the Q and R are the weighting matrices, and X reference is the reference state, and N is the prediction horizon in which we'll try to set. And X min and X max are the vectors of maximum and minimum and local values of the state variables. And U minimum and U maximum are the maximum and minimum and local values of the control inputs. These are our constraints. And after modeling the predictive model, we'll optimize the model using explicit quadratic programming. So the MPC problem can be converted into the quadratic programming problem, where the objective is minimize the quadratic cost function subjected to linear constraints. And so the constraints are already set here, and here the Hessian H and the gradient F are derived from the matrices A, B, Q, and R, where X is the state vector, which is the state of the vehicle at any time t. That's mass, position, the velocity, and others. And the U is the control input vector, which is the string angle and the differential braking. A and B are the matrices in the state space representation. A is a system matrix describing how a state changes, and B how the input matrix describes the input's effect on the state of the vehicle. So after optimizing the prediction model, we'll allocate a controller or a control action, which is determine the optimal set of control inputs that achieve the desired control effect U. Since we may have a lot of or number of actuators, we have to choose the optimal actuator to give in effect for the best actuation and control the state of the vehicle, which minimize the cost function that typically penalize excessive or inefficient use of actuators, and to minimize with this objective function and subjected to the linear constraints, one equality constraint and the other non-equality or inequality constraint in which the control inputs from maximum to minimum. Where Q is the symmetric matrix that weighs the quadratic cost of the control input, and the matrix can prioritize certain actuators over other or penalize using usage intensity. And C, the vector that may include additional linear cost or bias for using certain actuators if the optimized actuator which is set may not be efficient or enough. The C matrix or the C vector will give another actuator to come in effect for better control of the vehicle. And U, the vector of control commands for the actuators, and U bar, the desired control effect vector. So generally, the multi-input vehicle stability control flow diagram will be this. We have the system inputs, the state inputs, and the control inputs, and we'll model the predictive, we'll set the predictive model, and we'll set the optimization problem setup. So this problem setup will be optimized using explicit quadratic programming, and after having this solution, we'll allocate the will control allocation optimization problem setup. Then again we have to optimize the control location, and we'll go to directly for control action, and the loop will continue to control the vehicle in a stable manner. So the materials we'll use will be the MATLAB Simulink, and to validate our model, we'll use TrackSim, which is a standalone software basically used to test the performance of vehicles virtually. And in conclusion, this project proposes controlling the stability of a heavy vehicle using model predictive control to predict future vehicle behaviors, and then optimize the control inputs using quadratic programming, and then distributing these inputs across the various actuators through control allocation techniques. This will reduce the allowable incidents or enhance safety, and probably contribute to the advancement of vehicle and control technologies. And here are our references, and thank you.
Who's your advisor?
Professor Jerry.
Oh, Jerry, okay. So do you already have the truck simulation? Truck sim?
No, I will download.
Oh, you will download?
Yeah.
Is it free?
Actually, it's not free.
Okay. So there's the issue. There's a camera, I cannot say. So it's a very good problem, but how do you verify it? It's an issue. So if the simulator is not available, then I worry a little. Okay. Anyway, let's get back to the problem. Can you go? You have two quadratic problem. Can you show me the first one? So over, no, go down. No, down. Here.
Yes.
So over here, you already have objective function with UHU plus FU. Where are the x? What happened to the x?
The x already has
Has a value?
It has a value. So
x is the state of the truck.
the state of the truck. Yeah, and it's converted into.
Basically, for this problem, it's a constant already.
Yeah.
So what is the meaning for the objective function in this page? UHU plus FU. What is that?
H is the Hessian.
I mean, what does object function mean right here?
The object function here is to minimize, to minimize the cost function.
Yeah, what is the cost?
The cost here is.
What's the practical meaning right here?
Yeah, the cost here is to control the vehicle between the maximum and minimum inputs. Our inputs are the string angle and from the differential braking, which has.
So is it like a difference between your control and the desired state?
The desired state.
So basically, it's like a minimize error.
Yeah.
Okay. I hope you can formulate those more precisely, and because in control, every equation has a physical meaning. So, have you ever seen this kind of a two-stage approach in the literature already?
I see the approach, but I never see this stage altogether, but I see in a separate way.
Okay.
For example, control allocation with linear quadratic programming and MPC with another optimization technique.
I can see why you have a second problem when you allocate a new equality constraint and expect the control behavior to be as close to actually exactly equals to the desired state or desired control parameter. You have can you go to the next page? So you want your B times U equals to U bar.
Yeah.
So U bar is like a desired control effect, like you said. So whatever you do right here will be applied to what you had in the previous case.
In the prediction model, yes.
So it's like you have a driving condition. Before this, the previous page is like a regular control.
Yes.
And over here it's like for some kind of unique condition. So you need to apply a new constraint so that your vehicle will be driven in a certain way. You will behave like what you want. So this is more like a conditional formulation to meet some kind of a driving condition. So does that mean you don't need to turn this on all the time? If you have a straight road, you are driving smoothly, you don't need to do this. Am I right? Because if you are already driving the car smoothly, you don't really need to change your driving effect. So I guess this part, you don't need to run the second part.
What we need is control allocation. Is actually the previous stage by itself can control effectively the vehicle. But what we need here to allocate the control is we have two things to actuate: the steering and the steering and the differential braking.
So whenever you need to do something with the vehicle, you need a second part, I think. But what I'm saying is regularly, in the usual cases, when you are driving smoothly on the road, you don't need to solve optimization, just drive. So I guess in the next page, can you go to the next page? The left part of this flow doesn't need to turn on all the time. This is what I think. If you are driving smoothly, you don't need to change your control parameter. You don't even need the left hand side.
Yeah, sure.
So there must be a trigger. What is the trigger in the problem? What happened so that you need to run the left? What would you say?
Yes. Whenever we get the optimal solution for the first
From
phase
the right, okay.
from the right,
Yeah.
then we need to apply a controller, or we have to actuate any of the actuators in order to give or corrections to the right or the annual control action. So during this, we have so many actuators in the vehicle to apply. But one actuator has advantage over the other for different scenarios. Sometimes we may need to actuate the string than actuating on the differential, or actuating the differential may have more cost than actuating the string.
Okay.
So we have to choose the best actuator ever, or the best actuation setups. So the second part will work on that. Which actuator is come first, and if the first actuator will not manage the things, it has to.
So I guess on the right hand side, let's say you're driving and nothing changes. The road is the same. The speed, whatever driving condition is the same, and your foot is stay at the same speed. You do nothing. So on the right hand side, supposedly this is the best already. And all of a sudden, maybe you want to take turn right. So your driving condition changes. So maybe some of the parameter inside your vehicle, some sensor or whatever information, tell your system, hey, I'm turning right. So then that will trigger your system to solve a problem on the left. Your current U vector may not be the best.
Yes.
So since you're turning right, your system realizes you're turning right. All of a sudden, there is a desired vector U bar. So you need to quickly solve this quadratic problem so that you have a most appropriate control parameter so that your vehicle will behave like what you wish.
Yes.
So and if the left hand side can find a better control parameter, it will replace what you have so far. And if it doesn't, then stay what you have, I guess. So in this flow chart, there must be some kind of check, conditional check. Whatever this happened, then we do this. If this is better, then we replace it, or we keep the same. So I think this concept is good, but in the end of the semester, I'm looking for a detailed flow chart to properly explain about why this block is making sense, and then once you have that, then you should have numerical experiments to show whatever you are testing is working. And I'm not going to check whether your software is legal. But anyway, interesting topic. I think it will be quite challenging. Okay.
Yeah, it would be challenging, but I will try.
Yeah, please try. Okay. Any questions?
I see there are many functions used in the topic. Very functional formula. I have a suggestion for you. Don't just focus on the main scale calculation. Okay. If you do this, you will easy to lose when you try to optimization on the chart. Try to understand the physical characteristics in your formula or function or equation.
Okay.
Good morning, Professor, and good morning, everyone. We are the teammate. My name is Willie, and he is my teammate, Harry. And our topic is optimization of stochastic parameters for aluminum alloy composite production to determine the best mechanical properties using mathematical programming by Python language. And this is on our line. It's abstract introduction, literature review, research objective, and experimental methodology, and work plan and reference. And this is abstract. And a common process for creating aluminum alloy composite is stochastic, in which several production variables affect the end product's mechanical characteristic. The goal of this research is to find an optimal combination of stochastic setting that will produce aluminum alloy composite with the best mechanical qualities. The optimization problem is formulated and solved using a mathematical programming approach with the Python programming language. By varying the stir duration, speed, and pouring temperature, the goal is to maximize the desired tensile strength and hardness. Experimental information is gathered on the mechanical characteristics of the composites under various processing scenarios to use the mathematical programming paradigm and determine the ideal set of the parameters.
Okay. Thank you, Mr. Willy. For the introduction, we will preview the meaning of stochastic, and second, aluminum alloy composite, mechanical properties, mathematical programming, and Python. Okay, this is the literature review we already read from the paper. There is 6 of them. First is from Arunraj, 2017, is utilization of Takuchi method to investigate the effect of stochastic parameter. And then the second is Himalata in 2019 is similar with Takuchi experimental analysis, and then the utilization of principal component analysis to study of properties of aluminum composite. And then 2022 Abayomi is similar as Takuchi approach to find the optimal parameters. In 2021 Adilo using Minitab 19 software to predict the optimal stochastic parameter. In 5 Wijakumar in 2022 optimistic in Takuchi design using Minitab 17 by Anova. And then the 6th is Prasad in 2022 optimization using response surface methodology and central composite design to optimize stochastic parameter along with the statistic tools, mean square error, RMS division, ANOVA, and regression model. The research objective of this proposal is first, determine the optimal parameter of stochastic to reach optimal mechanical properties. There's just 2. First is tensile strength, and the second is hardness number. And we will develop regression modeling by mathematical modeling and equation to determine stochastic parameter. And the third is build Python script. So based on the introduction and literature review, we will this is our experimental methodology. First step. The second, we will continue the literature review and data collecting from the previous research. Then construct math modeling and equation, build Python code, and then validation, write presentation, and write final report, and then finish. Based on the scheme, this is the brand project for the optimal design. First week of May is literature review and data collecting. Second week of May is contract math modeling and equation. Third build pattern in the third week, and 4 write presentation. 5 is write final report. So this is our reference, and then thank you very much for attention.
Okay, one question. What are the design variables for stochastic?
First is...
Did you show it in the presentation?
Not yet, because there is 4, but there is variable as many.
Okay, so there could be 4 or more, right?
Yeah, 4.
So let's say you have chosen, I guess, very similar to some of the groups. You are going to build a list of variables, like a design of experiments, and then you are going to evaluate the performance. I guess you are testing the strength or hardness of your result. How do you get data?
So the data, first literature review that already, because they...
Are you going to get data from the literature?
Yes, from the literature.
So same issue as the other group. They are the group for ball milling. So they also, if you rely on data on the paper, then you need to make sure you have enough data. Okay, so your presentation is very similar to the ball milling group. At least they know what are the variables. In your presentation, it didn't show. And I worry about how are you going to work on this problem. Because I don't see any data source, or I don't see the formulation. And how do you verify the correctness of your project, of whatever you've done? So that would be difficult if you don't have data and you don't have I don't see a plan yet.
Yes, Professor.
Yeah.
That is because I'm not finished. We are not finished the.
Okay, so you better speed up.
Yeah.
Yeah, you can see there are some of the groups that are already doing something.
Yeah.
Yeah, you need to speed up. Okay.
I hope this week is already finished for
Yeah.
the mathematical modeling.
Okay, so if you need help, you cannot find me. You can find Dr. Patel. He's always there. Maybe he can help a little.
If you want to make like, I have a data of composites, biocomposites, like polylactic acid and fibers. I can give you that data, you can try with that data.
Yeah.
I have a different, but it's not say nothing, it's a hand-led method with various samples and tested for different parameters. You can give that data if you want.
Usually for data with experiments, there's an issue because once you find the optimal, you cannot test it because the experiment has been done. You are basically trying to get data from the past, and you cannot repeat at the optimal. So how do you know it's the optimal? So that's the issue. Okay. So please think more about what you are trying to work on. Okay. I really hope at the end, whatever you find is going to be helpful for your own research, and maybe at the end you can publish something. Right? Okay. Any comments?
Sorry, could go to the page about flow chart, right? Flow chart. I have a question about why you do the control mesh modeling first. Oh, sorry. Do the control mesh modeling and build Python code payroll.
It's not quite parallel actually, because after that, when we make a work plan, there is 1 week later.
I see you
No.
control mesh is
Yeah, this is not parallel.
modeling first.
First modeling and then
implement the mesh modeling on the Python. And if you fail on the Python code, you go back to the control mesh modeling. And
Logically, this flow is wrong.
Yeah.
Yeah. Okay.
Thank you very much.
Good. Okay, thank you. Next is concerning again.
Okay. Good morning, everyone. Good morning, Professor. And we are Group 9, and here is our title. We are going to optimizing component rods for wing performance. And our topic is to reduce the overall weight of the wing by optimizing the dimensions of the component rods in the wing. First, further reducing fuel or power consumption during flight. And first we will introduce the situation, then explain the optimization problem overview and optimization methodology. And at the end we will show our reference. So before we start, there's one thing we should all know is that the structure of an aircraft wing is not entirely solid. To reduce weight, the internal structure of the aircraft wing is made up of ribs, stringers, and carbon rods, which can fight against the force of lift and gravity. So this time we want to optimize the size of the carbon rods in the wing structure to reduce the overall weight of the wing. Therefore, we assume that we made our own UAV and that the aircraft is flying in a cruise mode, flying at a constant pitch angle and at a constant speed, which means constant lift. And the material use of the rods is carbon fiber, and the airfoil type use of the wing is NACA 4412. Then we try to figure out the optimal rod size of our situation based on our objective function and subjective.
Okay, so here's an overview of the optimization problem. Our goal is to minimize the weight of the carbon rod. So the objective function looks like this one. The cross-sectional area multiplies length and multiplies density. And these are our design variable. And we set 5 constraints. And the first constraint is tensile strength. And the second constraint, we want to check the root is hollow. And the third one is deformation. And the fourth and fifth are the size of the root. And we want to use these two optimize methods we want to use these two methods to optimize our problem and compare which one is the better. And here is my professor. Thank you. Thanks for listening.
Okay, can you go back to your formulation? So, are you going to run finite element?
Yeah.
Oh, really? Okay. If you're running finite element, then which part in your formulation needs data from finite element? Which part?
1 and 3.
The first one?
Yeah, and the
first one is stress.
Yes.
So you want the maximum stress to be
Yes.
smaller than some
My
limit.
materials.
But some limit.
Yes.
Okay.
And the
third one is what?
deformation.
A deformation.
We don't want the wing bending too much.
Okay. So one and first one and the third one, they are probably dependent.
Yeah.
So maybe you keep one, the other one maybe you don't need it. Either way.
Okay.
So from the viewpoint of mechanical design, you only need to worry about stress because
Yes.
failure is directly related to stress.
Okay.
And I guess to have a confined deformation is also good, I guess.
Yes.
So I hope those data are more practical, real data. So if you are you modeling this for like a real airplane size?
No, it's just
like a UAV size.
Yeah, like a UAV size.
Oh, okay. Are you going to build one?
No, I used to enhance my own UAV and use
Okay,
this
so
size.
so this kind of vehicle is it can be made, but you're not going to make it. You're
Yes.
going to just simulate.
Just simulate.
Okay, I see. Can you go down to your design for the carbon fiber rod? So basically, you are changing the diameter
Yes.
of the outer and inner diameter for the rod.
Yes.
Okay. So supposedly thicker rod will become heavier but stronger.
Yeah.
Okay. Is the rod all the way to the end, to the edge of your wing?
Yes, but actually it will two parts, left and right.
Okay, I see. So when you do simulation, I think you also need to simulate the whole rod and also the ribs, everything. Okay.
Yes.
Using ANSYS.
Yes, yes.
Do you already have the material property of?
Yes.
Oh, okay. I see. You have everything. Okay. If you use quadratic programming or GA, I think both of them will give you same result.
Yes.
I guess. And if you use GA, it will take a lot of time to converge because every trial needs one finite element.
Yes.
For GA, you need to run the finite element probably 1,000 times or even more. So you may not have enough time.
Okay.
Maybe this is very
Okay.
So maybe you can try the Smart 2. It's easier.
Okay.
Because you are running finite element. If you are manually adjusting the parameter, it actually also takes a lot of time.
Okay.
Yeah.
Okay.
So think about this.
Okay.
But if you won't use Smart 2, then where's your contribution? So there's always an issue. If you try to work on the problem by yourself, that takes a lot of time. If you rely on a software, then you have no contribution. So for this kind of proposal, that's where the issue is. Yeah. In the past, when I was a student, I also wrote a MATLAB code to work with ANSYS. So my contribution was the MATLAB code.
Yes.
And that MATLAB code will generate finite element script. So it will automatically call ANSYS and run the finite element, and then get the result back. So then my entire package will automatically run finite element. The MATLAB code do optimization, finite element get the performance. But if you want to do that, it's very difficult. When I was doing this, my finite element model was very simple. You're doing a very nonlinear geometry, so maybe you need to rely on the Smart 2 commercial software. Yeah, that's what I guess.
Okay.
That's what I guess. But if you are trying to use Smart 2, maybe you can think of more scenarios or different design parameters for your auxiliary function. You can try to work on different problems, make the scenario as realistic as possible. Okay, that's what I suggest.
Okay, thank you, Professor.
So after this week, whenever you have any questions, you can come to me and discuss with me. Okay?
Okay.
Okay, thank you.
Thank you, Professor.
Okay, next is Jia Lun and Zheng Huan.
Good morning, everyone and Professor. My name is Vera, and this is my teammate Ella. And our project topic is dynamical and bio-inspired path planning methods with robotic arm. And this is all that. First, we will introduce our project. Second, we will introduce Dragonfly's path planning method. Third, we will introduce our experimental setup and path planning with optimization method. Finally, we will introduce the expecting result. And here is our project motivation. Based on the strength of the automatic industry within the robotic arms with high potential, Hence, we want to explore path planning for robotic arms and integrate optimization techniques into our project. Our goal is to define a module that can rapidly get the best moving paths and avoid dynamically shifting obstacles. These path planning methods can reduce loss of resources and time costs. What is path planning? Path planning aims to find the most efficient route from the starting point to a destination while avoiding obstacles or constraints along the way. Here are some applications of path planning. First is autonomous vehicles, such as HV and AMR. Second is mobile robots, such as robotic arm. Third is game development, such as the NPCs walking paths in the game. And the last is the drone swarms, such as UAV. And here are different types of the path planning. First is A-star and PRM and BIRT. And for the bio-inspired algorithms is such as ant colony optimization, dragonfly algorithm, and artificial bee colony. In our project, we choose the dragonfly algorithm as our path planning method. It is a nature-inspired optimization algorithm that mimics the hunting behavior of dragonflies, and it is designed to solve optimization problems efficiently, especially those related to swarm intelligence and evolutionary algorithms. This method is suitable for a variety of optimization, such as dynamic optimization, high-dimensional optimization, nonlinear optimization, and constraint optimization. According to its characteristics, we decided to use Dragonfly optimization algorithm as the global searching method to find the initial path and add Newton's method as a local optimization method to smoother the path in a dynamical obstacle environment.
Good morning, everyone. My name is Alan. So, wait for a sec. So this is our experimental set. The software we will use Python, MATLAB, and Epson robot. Our optimization path planning method will be Dragonfly algorithm and Newton's method. The detail of our experiment is that the dimensions of the path is 2 dimensions. The start point and end point will be randomly assigned. Also, the articles will be randomly moving and sizing. Our goal is to get real-time detection of obstacles and path correction. Meanwhile, minimizing the moving distance and time cost. This is how we carry out the path planning. First, use the Dragonfly algorithm to obtain initial path points. Then we incorporate Newton's method and mean square error to derive multiple equations for the path. This not only allows for smoother path, but also for immediate correction of path when encountering obstacles, and ensures the shortest distance and time to reach the target point. And forgive us that we forgot to put the formula. So we got n point from Dragonfly algorithm. Then we want to find out the multiple equation of our path. So we use mean square error and with and Newton's method, and the parameter will be decided by us, and also the points will also decide. This is our flowchart of our experiment process. Simply to say, we will apply Dragonfly method for initial point of the path in the beginning. Then we will combine Newton's method. After that, we will test the code and simulate the result. For the next process, we will modify the code for robotics arm and integrate our method. Before running the process with big obstacles, we will simulate the robotics arm's path For here, why do we use fixed articles? Because we think that using fixed article is easier to debug the code and adjust the parameters. After running the process, we will record experimental data and adjust the parameters of experience to do the process again. Then compare all the data and define the best parameters of the patch panning. In the final part, we will test for the dynamically shifting articles, then finish patch panning model. And expected result, or it can be conclusion. We will present the results of simulated patch panning and videos demonstrating real-world validation. We aim to derive the mathematical formula for the patch panning algorithm by integrating the Dragonfly patch panning method with optimization algorithm. We will identify the key factors influencing movement time and distance. And our objective is to develop a patch panning method that minimizes both the time spent and distance traveled to reach the goal point in a dynamically shifting optical environment. And this is our reference. Thanks for listening.
Okay, interesting approach. Some questions. Since you are solving a 2D problem, I guess you are going to move your robot arm and allow the end effector to move along some kind of puzzle, right? But when you do that, it's actually dangerous. Because let's say this is an obstacle. Your robot arm can hit the obstacle. So I guess the more practical way is to have a piece of paper print out the obstacle and try to move along the puzzle so it's impossible to hit the piece of paper. If that's the case, you don't even need to use a robot. That's not the robot is not important anymore. So I guess the main focus will be you trying to use the Dragonfly approach to find the optimal path. And you are not even formulating any constraints to avoid collision. If you want the robot part to be more important in your project, then you need to solve a 3D problem. You need to always check the shortest distance between obstacle and the robot arm, entire arm. So during the movement, is there a danger, possibility for collision? So that would be more practical, but that takes a lot of time to so you need to decide what you really want to work on. If you are only solving a 2D problem, then I don't think you really need to use an absent robot to test it. I mean, we know if you have a trajectory, Epson will move along the trajectory properly. So then if you are just demonstrating that, then don't spend time on it, unless you are truly doing 3D. So that would be my one recommendation. Second thing is, I recommend you not to do a two-level approach. So you use a Dragonfly to find endpoints, and then you use Newton's method to find the best fitted polynomial. That's wasting your time. So go find something called B-spline. B-spline. In Chinese, it's called 圆形线. So B-spline is a kind of cubic curve with multiple control points. The cubic curve will have a smooth trajectory controlled by those points. So Dragonfly can be the method to find the control points. And the B-spline already pass along that curve. Then you don't need a Newton's method. Because if you use Newton's method at the end, your trajectory will not pass through all the points. It's just an approximated curve. Then why bother use Newton's method? Just use B-spline. The issue is you need to learn how to formulate B-spline. You need to learn how to do it. It's a little difficult to understand. It's difficult to learn. It's a lot of math inside. Once you know what's going on inside B-spline, then you can. It's actually pretty useful. Okay, so I'm quite interested in how the dragonfly can find the trajectory. But what is your objective function? So let's say you have a set of curves, and you have another set. Which one is better? How do you rank? What's the score? Time cost. Maybe shortest distance. Shortest distance. Okay. Okay, sure. And also, if you want to make this problem a little complex, you can set up some constraint to keep a certain distance away from the obstacle. So your points has to have certain distance away from it. So in your function, there is always an equation describing any point on the curve that the distance between any point on the curve with the obstacle. But that would be a little complex because your dragonfly algorithm needs to evaluate more functions. So think about those. Forget about the robot. You don't need to work on the robot. Okay? Any comments?
Just follow Professor Lin says, you can take a robot to be a point to optimize the pace. Because if I control a robot to go to here, maybe robot will be this way or this way. And then if you do this way, you will hit something. This way, it doesn't hit something. So you can take a robot as a point, like HV. HV can be take a one point, rigid point to optimize the pace.
Okay. Okay, thank you. So the final team is Nelly and Aichi.
Hello everyone, we are team 11 and the presenter is Shikaichi and Nelly, and the topic of our project is optimization of the tilt angle of solar panels. Why this topic? Nowadays, Taiwan is facing a shortage of electricity. Apart from thermal power generation, there aren't any other energy sources available to substitute or provide a substantial amount of energy. So we hope to enhance the efficiency of solar panels by identifying the optimal angle for solar energy orientation and continuously adjust the panel angle in real time to ensure they always face the sun.
Yes, so why isn't it so easy to find the best orientation? It is because there are some outer constraints which affects this. One big constraint is the sun position. The sun position changes throughout the day, throughout the season, and also depending where you're currently situated. And another big point is the weather. Of course, when we have clouds, the sun radiation will be less than if we have a super sunny day, and temperatures can also affect this. And of course, which PV type you will choose. Yes, so here we can, for example, see how the sun position changes throughout the year. You can see the angle at which it goes to your location is different. It actually changes by 23.5 degrees from average during wintertime and summertime. And on the right-hand side, you can see, for example, how the PV model therefore has to be directed. So we have to change the tilt angle to still get maximum output of energy. So our goal is to find the optimal tilt angle and also orientation for later problems for multiple scenarios to maximize our energy output. So first of all, we want to create a 3D plot which visualizes the energy output over our tilt angle beta in dependency, for example, of the time of the day, so where the sun position is, then also how the declination angle changes throughout the year, which effects the sun radiation has, and also visualize it for an average year, for example, in Taipei, where we consider the temperature, the sun radiation, and also the declination angle of the sun. So in our project, we want to do multiple levels to step-by-step increase the difficulty. First of all, we want to calculate the optimal tilt angle. In theory, this is not very hard. Then we want to also take the weather into account. The third level is where we actually start with the optimization. We want to reorientate our solar panels 4 times a year. This is a number we found out in literature. And then find out at which tilt angle and at which time of the year should we reorientate our PV angle. And if we still have time and resources, we also want to consider minimum interrow spacing. So thinking about, okay, which effects does the shade of each solar panel maybe have on the other solar panels if we only have limited space? How should we, how big should the space be between each row? And also, if we have a limited space with a certain orientation, at what orientation should we put the solar panels to also, again, get the maximum energy output? And here you can see our first ideas, how we want to calculate these things. The optimal tilt angle, if we don't consider any weather or anything else, is quite easy to calculate. If we want to take the weather into account, basically we have to calculate the radiation, and in this radiation calculation thing, we can also input our tilt angle and find the maximum output energy. And for level 3, we need to find for different tilt angles and also for different time slots at which the tilt angle will be orientated. For level 4, we have to give a certain limited space to find our optimal tilt angle, and in level 5 we also have to input a limited space and also the orientation of the space.
In the lab is our schedule, and we want to do is to read the literature review to gather data. Next, we'll get to know Python libraries and to find the property library to use in our project. And next, we'll optimize for theoretical conditions. Then we optimize for real weather conditions. The final will to calculate the number of reorientations. And that's our proposal. Thank you.
Okay, so are you going to build one device? No?
That wasn't planned yet.
Okay, so if you are not building one, how are you going to get data? So everything will be by imagination or by just mathematical assumptions?
No, we want to get the weather data, which was collected over several years,
Okay, so basically historical data.
Yes.
But historical data doesn't tell you what's the weather today.
No, but we don't want to reorientate our PV model like every day, just as a suggestion, like how can PV models, for example.
So you just want the device to move based on the best positioning or orientation based on the historical data.
Yes, so first of all, I calculate the theory, what would be the best angle for each day, but then have this constraint, okay, we only want to reorientate our PV model 4 times a year. How could it be?
Okay. Do you have historical data with you?
Not yet. I've got a friend who's doing research in this, and he said he can provide us with that, and we're talking about that.
Based on my understanding, usually they have a sensor on the PV panel, and then they basically move around to find the orientation for the sun.
Okay.
Yeah, usually that's where you can get the maximum energy of storage, right? Greater radiation.
Yeah, yeah.
So if it's a cloudy day, you basically do nothing because low radiation.
Yes.
Yeah. If it's a rainy day, maybe you just turn off. Don't waste your energy. Don't waste the power for motor, I guess.
Yes.
So then you have very little things to work on in the project. So my worry is it's a very important topic and very practical, good for the earth, but it's hard to showcase what you work on in the project. So how about this? In my lab, there was a device. I'm not sure if the device is still there. The device was made like a gimbal. Do you know gimbal? So it's like a stabilizer for the phone.
Okay.
So usually that kind of device can be used for hand stabilizer. So when people taking pictures, if they're running, it's gonna be steady. Or they place it underneath a UAV, so when the UAV flies, the camera is still stable. So the device is called gimbal, and usually it has it controls 2 angles only. It doesn't need to control 3 angles, I think. So we have a device like that, made by my student. It was made for surveillance. So the goal was to do image processing and then, okay, here's a bad person, okay, I take a picture. If the person moves, the camera moves with them. So the device is, if you are just, maybe you can play with the device and see if you can make the device to point to the sun all the time. And maybe there is a optimization inside, so you allow this device to move around like our iteration process. You keep on moving until you find how do you say, the position with the strongest sun. So your RGB function would be maximizing the brightness of the picture, something like that.
Okay.
So in that case, you use it as a practice to mimic how you work with the solar panel, but you don't truly have a solar panel. You have a moving camera.
Yeah.
Or later on, you can switch this to a different application, really work on like a surveillance or something else. Basically, you are having a pitch roll and yaw control system and aiming on some kind of target which moves. And inside, you use optimization to control its movement. And you have something really to work on. Yeah, so I go back to figure out where the device is. If we have it, maybe you can use it as a starting point. Okay? Any comments? Okay, thank you. great. This time we have 11 groups, and every group presented something either related to your own research or something you're interested in. I really enjoyed what you presented, and I gave you guys some comments. If you need more comments from me or some help, you're welcome to come find me. If you cannot find me, find Dr. Patel. He's always in my lab. At the end of the semester, I hope you can show something, showcase what you have done for the semester. The key of the project is about optimization. So if you cannot find a very good performance of your problem, but you still can show what you have done for optimization, that's good. Because the importance is optimization. So that's why I keep on asking you, do you have data? Or because I don't want you to spend a lot of time to generate data. That's not the main purpose. That's all that you can. You don't need to. For example, someone is building an airplane. Don't build an airplane, okay? Yeah. So I guess you get what I mean. Focus on optimization, and if it can help you solve some problem, and that problem can truly be published somewhere, I will be happy to help. Right? So that's that's the end for today. Any questions from the students? No questions? Okay. So keep working hard. I hope everyone gets something you are looking for at the end. Okay, thank you. Bye bye.